we have three main states of matter: gas, solid, and liquid. And gas is the simplest one of them. There is no intermolecular forces between the gases. So that's why, again, air, for example, we're just walking through air, nothing is happening because there's no intermolecular forces between the molecules. You can swim in water, but you will have a resistance because of the intermolecular forces between the molecules. You cannot definitely swim in solid. Solid has very strong intermolecular forces. The molecules are so connected to each other and so close to each other. So just to give you an idea how the strengths of how the molecules attract each other physically around us. You cannot hold the gas. The gas will occupy the whole volume. Doesn't matter what the volume is, the gas will occupy that volume. Again, when you're looking at the pressure exerted by the gas, the pressure exerted by the gas is the collision of the gas molecule in the container wall. The more pressure, the more collision on the walls of the container. How we determine that pressure? Force per unit area. So force per unit area, that will be how we determine the pressure of the gas. Since we're dealing with pressure, there are multiple units for pressure. Here are the different conversions for the pressure. The SI unit, which is a standard international unit of pressure, is Pascal. Here is the conversion between the atmosphere and the millimeter mercury. 1 atmosphere equals 760 millimeter mercury. Here is the conversion between the torr and the millimeter mercury. So again, different conversions, different units. We developed multiple gas laws. This gas laws was developed based on ideal gas behavior. An ideal gas behavior means there is no intermolecular forces between the gas molecules. The gas occupy the whole volume. So this is again represent an ideal behavior. So what are the variables that we're going to basically develop these gas laws? These variables are pressure. The gas is going to be affected by pressure, either increasing pressure or decreasing pressure. Temperature. The gas is going to be affected by increasing temperature or decreasing temperature. Volume. The gas is going to be affected by increasing volume or decreasing volume, and the number of moles. The same thing. More number of moles will represent a different behavior for the gas than small number of moles. So these are 4 different experimental variables that result with 3 different gas laws. But before we talk about these gas laws, let's talk about the kinetic molecular theory of gases, the framework of gases. What's a gas? A gas consists of tiny particles, either atoms or molecules, moving about at random. The volume of the particles themselves is negligible compared with the total volume of the gas. Most of the volume of the gas is empty space. As I said, the gas will occupy the whole volume. The gas particles act independently of one another. There are no attractive or repulsive forces between particles. They don't attract each other and they don't repel each other. Collision of the gas particle is going to be elastic collisions. An elastic collision means the molecules just collide with each other and go in their own way. That's an elastic collision. Like a 2 tennis balls hitting each other, basically they will collide with each other, but then they will go in their own way. They don't become one body. The average kinetic energy of the gas is proportional to the temperature. As you increase the temperature, you increase the kinetic energy of the gas, which makes sense. If you have carbon dioxide dissolved in water, which is soda, the soda can, you open the soda can and you leave the soda can open for a while and the temperature starts increasing, the gas is escaping from the water, and pretty much the soda no longer, and after 1 hour, 2 hours, if you just leave it out there, it's no longer basically a soda, it's just basically water because the gas has escaped. The speed of the gas will depend on the molar mass. So the average speed of the gas will depend on its mass. The smaller the mass, the higher the speed. The smaller the atom, the higher the speed. So look at hydrogen gas. Hydrogen gas has the highest speed compared to any given molecules because it has the smallest molar mass in the periodic table. Hydrogen H2 has 2 grams per moles. That's the smallest molar mass in the whole periodic table. So hydrogen is going to be the fastest compared to helium, to water. So as you increase the molar mass, looking at the x-axis here, as you increase the molar mass, the average speed increases. So if you have a tank, that tank is containing hydrogen and helium, and there is a leak in that tank. The hydrogen is already escaping in a faster rate than the helium. So this is very dangerous because the tank is no longer containing the hydrogen. The hydrogen is already out there, and hydrogen is a highly flammable gas. Helium is inert, but hydrogen is a highly flammable gas. So that's why it's very important to understand the chemistry of gases and, again, the physical nature of the gas. Look at carbon dioxide has the least average velocity or average speed because it has the highest molar mass here. We have 3 gas laws. The first one is Boyle's law. So Boyle's law, which is a relationship between the volume and the pressure. And this relationship is an inverse relationship. When V is proportional to 1 over B, this is known as proportionality. When V is proportional to 1 over B, that's a reversible or again, inverse relationship. So this is an inverse relationship. What this mean? I mean, if you increase the volume, you decrease the pressure. If you decrease the pressure, you decrease the volume. So they're opposite to each other. So here is the pressure and here is the volume. And this is the inverse relationship. As you can see, at high volume, you have low pressure. At high pressure, you have low volume. So you can see the relationship is an inverse. If you plot V over 1 over B, you'll get a straight line. When you plot this, you'll get a straight line because they're opposite again to each other. V will be direct proportional to 1 over B. And if you plot V versus B, you will have this inverse relationship. So how you represent this in 2 different data points. If you have the gas initially at 1 atmosphere and 1 liter, then you increase the pressure from 1 atmosphere to 2 atmosphere. What's going to happen to the volume? The volume is going to drop in half. If you double the pressure, you're going to decrease the volume by half. This is how the relationship is. This is how the inverse relationship is. If you double the pressure, you're going to decrease the volume by half. So this was 1 liter, it become 0.5 liter, and that will be compression. So what you're looking at from V equal 1 liter to V equal 0.5 liter, that's the compression. Compression means you're compressing the gas. If you decrease the pressure, if you go from this condition here, where the pressure is 2 atmosphere, the volume is 0.5 liter, to this condition here, you're decreasing the pressure. If you decrease the pressure by half, you double the volume. Again, this is an inverse relationship. So if you decrease the pressure by half, you double the volume. And this is what Boyle's law look like. B initial, V initial will equal B final, V final. So this is our, again, relationship. And this is, again, Boyle's law. And this was carried at constant temperature and number of moles. You have to make the other variable constant when you're studying the relationship between 2 variables. So studying the relationship between the pressure and volume, the temperature and number of moles will be constant. The second law, which is the Charles law. So volume versus temperature at constant number of moles and pressure. And you can see the relationship is direct. This is the difference between boils. Look at the boils, it's an inverse. And look at the Charles, their direct relationship. How we express Charles' law mathematically? The V initial over T initial will equal V final over T final. So if you are working at 1 atmosphere at 200 Kelvin and 0.5 liter, and you heat this gas from 200 to 400, what does this mean? Mean you double the temperature, you're going to double the volume. It's a direct relationship. You double the temperature, you double the volume. And this is why this relationship will, again, will be valid. V initial over T initial equal V final over T final. So Avogadro's law, which is the volume versus number of moles. So as you increase the number of moles, the volume is going to increase. If you have a lecture with 50 students in a certain space, if you have 100 students, you need to increase the space. If you have 200 students, you need to increase the space further. So the volume is going to increase as you increase the number of moles. Remember, the number of moles is a direct relationship to the number of molecules. So as you increase the number of moles, you need more space. So the volume will increase. So that's, again, Avogadro's law. And here is the model for that. V initial over N initial will equal V final over N final. So these are the three gas laws. Again, Charles, Boyle's, and Avogadro's, and we can summarize them here. So here is Boyle's law, here is Charles' law, and here is Avogadro's law. With a system, and if the system is gas, then you can apply the gas laws on this system. So the ideal gas law, which is also known as the universal gas law, is the relationship between the pressure, the volume, the number of moles, and the temperature. So what is R? R is a gas constant or the universal gas constant. And it has two main units. These two main units are heavily used in chemistry, either the units that has the atmosphere and liter, or the unit that has the joule. The joule is the standard international unit. So what is the joule in terms of pressure and volume? Pressure has to be Pascal, volume has to be meter cube. So if you have the pressure in Pascal, which is the standard international unit of pressure, the volume has to be meter cube. Meter cube is the standard international unit of volume. If you multiply these two, you will get the joule. So this will be used when you have the pressure in Pascal, the volume in meter cube. This here will be used if the pressure in atmosphere and volume in liter. So clearly you can tell from the unit what is the pressure unit and the volume unit is. So what is the Kelvin relationship to Celsius? The Kelvin equals Celsius plus 273.15. So 273.15, this is the 0 Celsius, which is 273.15 Kelvin. And if you have any other temperature in Celsius, you will add 273.15 to that. There's another form of the gas law that's also not mentioned quite often in gas. And this is very important. Why? Because if you are working at two different conditions, initial conditions and final conditions, what does this mean? Mean your pressure is changing, your volume is changing, your temperature is changing. Then you cannot just simply use BV equal an RT because this is one data set. This is a one data set here. Pressure and volume and number of moles and temperature, this is only one data. This one here is two data sets. You need the pressure, you need the volume, you need the temperature. For example, a balloon. If you're riding in a balloon, this balloon going higher in altitude, the pressure is changing, the temperature is changing, the balloon volume will change. You're diving. If you are diving again deep in the ocean or again in water, the pressure change, the volume change, the temperature change. If you're hiking up in a mountain, the pressure change, the volume change, the temperature change. So as you can see, This here applies when you have two data sets or two data points. How to determine the volume at STB? What's STB? STB is the standard condition of temperature and pressure. What is the temperature for STB? Here is the temperature, 0 Celsius, which is 273.15 Kelvin. What is the pressure? 1 atmosphere. So this is the standard temperature and pressure for gases. For liquid, this is different. This is 25 degrees Celsius. But we're looking into gases right now. We're not studying the liquid phase. Number of moles is 1. That's the standard condition. The R is 0.082058, which is liter atmosphere per Kelvin mole. Temperature is 273.15 Kelvin. Pressure is 1 atmosphere. That's why we use this unit of R. If you do the mass here, the standard volume is 22.414 liters. What does this mean? It means if you have 1 mole of any of these gases, 1 mole of any of these gases, regardless what the gas is, they're going to occupy the same volume. And that volume is going to be the standard, again, STB volume at 1 mole, which is 22.4 liters. So any of these will occupy that. What is the application of gas laws? I just explained to you multiple application to gas laws. Multiple application in hiking, when you're hiking, when you're diving, when you're, again, balloon at different altitude. This has become very important because it can tell you information about what's happening to the condition that you're under. Every time you're dealing with a gas, this law becomes very important and you can obtain very useful data. So how can we use this law in quality control? And in particular, in automotive. Remember, the automotive, the car, our cars has an airbag. How do you think this airbag function? The airbag is basically containing a solid. That solid, when a collision happens, and that collision is enough to trigger, again, that decomposition of that solid. What that solid does, it undergo this decomposition where it converts to sodium, which is solid, and then the gas, which is filled the airbag. So this is the mechanics of the airbag. First of all, that reaction has to be triggered. That reaction is triggered by, again, as I said, a collision that's sufficient enough to trigger that. And that all of this is engineered. What will trigger that? And, but our chemistry point of view, how can we quality control this? What I mean by quality control, you are dealing with a volume. You're dealing with an airbag that is going to be, again, inflated. And it's going to be inflated with a gas. That inflation or that filling of the gas depends on the mass. So you're backing the airbag in a specific car. The airbag has to go through testing. And it has to go through stoichiometric calculations. So Chem 101 is quality control in this particular plant. As you learn in chapter 3, whatever you have in your chemicals reactant is going to convert to product. So how can we determine the volume if we backed 45 grams of this? If you have 45 grams of this, how much volume that will correspond to nitrogen gas? And we can use, again, BV equal nRT to determine that. Our condition is the pressure is 1.15 atmosphere. The temperature is 30 degrees Celsius. So you have, this is your chemical. This is your reaction. And your reaction is producing a gas. And you want to determine the volume of the gas based on the mass that you put in. Because this mass will reflect on the volume. So step 1, stoichiometric calculation. Chapter 3, one more time. Even though we're finalizing that course, we're still talking about chemical stoichiometry. You cannot forget what we learn in any chapters because all chapters are basically telling a story. And as Chem 101 is being scattered because it's covering multiple topics, you still have two main topics. One, which is stoichiometric and chemical reactions, and the other topic is atom first model and again, type of bonds. So this is pretty much the breakdown of Chem 101. We have two sides. The first topic is chemical stoichiometry and whatever apply under that. And the second part is the atom first model and whatever apply under that. And we have covered multiple chapters in regard to this too. So here we're covering basically how to use stoichiometry to determine the volume of the gas. So here is our mass of the given. If you recall chapter 3, this is the given mass. Here is the conversion of grams to moles. Remember what we do to grams? We convert it to mole by dividing by the molar mass. Then we multiply by the mole ratio of the nitrogen gas to the sodium azide. This is known as sodium azide, 3/2. And that will give us the moles of nitrogen. So now from this, I got the moles of nitrogen. By conducting stoichiometry, we get the moles of nitrogen. Once we get the moles of nitrogen, I can use BV equal nRT. I can use this. I have the pressure. I have the number of moles. I have the temperature. R is known. I can calculate the volume of nitrogen. So the volume of nitrogen will equal the number of moles, which is 1.04, times R, which is given, times the temperature in Kelvin. This is where the quality control is. If somebody did this calculation based on the 30 degrees Celsius, then this is going to be a very big problem because your volume is not related to 30 degrees Celsius. Your volume is related to 303 Kelvin. So you're underestimating the volume of nitrogen. And by underestimating the volume of nitrogen in an error, this is an error in the calculation, you're going to request to add more solid because you're getting an under value. So this equation matter. The value matter. This is life-saving. And if you underestimate the volume or overestimate the volume, lives can be at risk. Because if you overestimated the volume, this is not going to save the driver or the passengers, this is going to crush them. And if you underestimated the volume, this is not going to save them because it's not going to be enough to give that safety net to prevent, again, serious damage. So it become very important. And you can see here chemistry in real life, real situation in quality control. All right, so it's very important this applied correctly because this value will represent what you're applying here. So here's the number of moles, here's R, here is the temperature in Kelvin, here is the pressure in atmosphere, and here's the unit of R in atmosphere and liter. So here is the volume, 22.5 liter, and you will evaluate that based on the size of the car, and again, if this enough or you need to have more solid. The more you add solid, the more the volume will be higher. So this is again chemical stoichiometry as we know it from chapter 3.